one. In the previous class, we were doing an example where we were trying to find the CDF of a function which was split with respect to the domain. So the first thing I'm going to do today is I'm going to clarify that part. The mistake we were making was something like this. And then I will summarize the things. Your f of x was it was 0, let's say below 0, and it was, let us say, 0.25 between 0 and 2, and it was 0.5 between 2 and 3, and it is 0 above 3. Let us say your PDF is like this one. So if you want to find the CDF of this one for the split function, the CDF f of x, that will be simply 0 for x less than 0. It will be for 0x less than 2, the CDF will be integral 0 to x 0.25 dx, and that will be 0.25x. The mistake we were making was here. For 2 less than x less than 3, your CDF should be from 0 all the way up to 2, 0.25 dx plus 2 up to x, 0.5 dx. We were not starting, we were missing this part in the last class. This part was missing in the second function. You always have to start the CDF from minus infinity. That is, for this question, you'll have to start it from 0 all the way up to x. And we know that from 0 to 2, the function is 0.25. So this whole part, I think this will be 0.5. This will be 0.5 plus this will be 0.5x all the way from 2 to x. So it will be 0.5 plus 0.5x minus 1. So that should be 0.5x minus 0.5. So this should be your CDF, 0.5x minus 0.5 from 2 all the way up to 3, and above 3 it is 1 simply. This is how you will find CDF. And in this CDF, now you put 2 in either of these two portions, you should get the same value. This is the correct CDF. And I think in the last class we were doing it for 0.5, 0.5. The function was same for both of them. So this green part was something we were missing. Okay, now I will summarize the things that we have done so far. The summary of the continuous random variable is as follows. We talked about the continuous random variable, and we said the general case is the case where we have the PDF of x given as x following a function over a specific domain, such that this function possesses these two properties. Then using this function, we said we can find the several properties of x, including the mean, the variance, We can also find the distribution function of x, capital F of x, using this small f of x. That is, you integrate from minus infinity to a specific point x, and you will get a function, and this function is basically the probability of x less than equal to that value. Using this CDF, you can find several percentiles. That is, you can find median by using capital F of median equals 0.5. You solve this equation and you will get median. Similarly, if I ask you to find first quartile, you will solve F of Q1 equals 0.25. This will give you the first quartile. If I ask you to find the third quartile, for example, you will solve this equation, capital F of Q3 equals 0.75. If I ask you to find, for example, P60, 60th percentile, so you will solve F of P60 equals 0.6. And so on. In general, if you want PI, you will solve this equation. Also, this capital F of x can be used to find the probabilities. The probability of x less than equal to a is simply capital F of a. The probability of x greater than a is 1 minus f of a. And the probability of x between a1 and a2, that will be capital F of a2 minus capital F of a1. This is all that we have done so far. If you have any question out of all this general case, you may go ahead now. Okay, in case there is no question, I'm going to go specific with special distributions now. Like we discussed the general case in discrete random variable, and then we discussed 4 or 5 special distributions. Those were discrete, uniform, binomial, negative binomial, hypergeometric, and Poisson distribution. Similarly, in this chapter, I'm going to go towards some special distributions. And the first of those special distributions is continuous uniform distribution. A random variable, a continuous random variable, is said to have following a continuous uniform distribution if its probability density function is having this form, 1 over b minus a, where x is between a and b. For such a random variable, the mean of x is given as a plus b over 2, and the variance of x is given as b minus a whole square over 12. These expressions will be given to you in the formula sheet. And for such a random variable, the CDF is also given in the formula sheet, that is x minus a over b minus a. Let us have a question. Mostly, if you see a question from continuous uniform distribution, they will use the word continuous uniform in the question. But if you don't see the word, the only trick I see from this distribution can be if the density of any question is constant, no x in the density. If it is constant, it is uniform. That's the way to recognize it. If the density of any variable is constant, f of x equals to a constant value, that is uniform. So let me copy an example from the book. Okay, let us try and see what we can do with this example. This example 4.9 from the book says that the random variable x has a continuous uniform distribution on interval 4.9 to 5.1. Now, even if this second statement is not given, you should be able to solve the question. If I stop the question here and I don't give this green part, you should be able to write the probability density function by yourself. Look at the probability density function formula from the formula sheet. It is 1 over upper limit minus lower limit. So when they tell you that x is from 4.9 to 5.1, you should be able to write that f of x is 1 over 5.1 minus 4.9. You don't need this green part. You should be able to write from here that f of x is 1 over b minus a. And this should be 5, I think, where x is from 4.9 all the way up to 5.1. This is the first thing. The second thing I may ask you is to find the average current. Find the average current. So if I ask you to find the average current, that should be mu of x, which is b a plus b 4.9 plus 5.1 divided by 2. This is 5 milliamperes. If I ask you to find the, for example, variance or standard deviation, let's say I ask you to find the standard deviation, you should plug in the values b and a into the expression, that is b minus a whole square over 12. Whole square root should be the standard deviation. So it is 5.1 minus 4.9 whole square divided by 12 whole square root. And this comes out to be 0.0577 milliamperes. If I ask you to find some probability, and before probability, if I ask you to write the capital F of x, you should be able to write it from here. Let me copy it. It's x minus a over b minus a. So it is x minus a over b minus a. And this I think is 5 times x minus 4.9. That is the CDF. From the CDF, now you can find almost everything. For example, if I ask you to find the probability that x is find the probability that x is less than 4.95, you should be able to find, this is capital F of 4.95. So you just plug in 4.95 into the function and you get 5 minus 4.95 minus 4.9. So that should be What is the answer? Can anyone tell?
0.25.
0.25. If I ask you to find the probability of x greater than 5.01, that is 1 minus capital F of 5.01. Greater than probability is 1 minus capital F. So that is 1 minus 5 times 5.01 minus 4.9. So this is 1 minus
0.55.
0.55. So you should get 0.45. And if I ask you to give me probability of x between 4.95 and 5.01, this is capital F of 5.01 minus capital F of 4.95. The CDF at the bigger value minus the CDF at the smaller value. So this will give me 5 times 5.01 minus 4.9 minus 5 times 4.95 minus 4.9. Final answer. Yasir Abdo, please go ahead with the question.
But is it x less than or equal?
Less than or less than equal doesn't matter in continuous. I'll not take care of this.
So they're the same.
Yeah, if I put equal sign or I don't put equal sign in continuous random variable, it doesn't matter.
Okay, thank you.
Muhammad Faris.
Yes, the answer is 0.3. And I have a question, please.
Yes, go ahead.
Why, when we have like greater than or equal, always we put 1 minus?
Greater than or equal to by definition is 1 minus CDF. That is, if you require probability of x greater than a, I can write this as probability of x less than equal to a, right?
Yes.
And this by definition is capital F of a. Capital F of something is less than equal to probability.
Yes, this is the complement.
This is the complement, yes.
Yes, I understand now. Thank you.
Yes, greater than probability is the complement of CDF.
Clear, thank you.
What if I ask you to find Q1? What if I ask you to give me the first quartile? You can find the first quartile like solving this question. Capital F of Q1, you put it equal to 0.25. You solve this equation and you will get the first quartile. So capital F of Q1 should be Q1 minus 4.9 divided by 5.1 minus 4.9. No, I think we simplified it. 5 times this one and put it equal to 0.25. Now you solve this equation for Q1. So your Q1 will be 4.9 plus 5 times 0.25, which is
4.95.
no, I think it's divided by 5. 0.25 divided by 5. Yes?
Yes, 4.95.
4.95 milliampere. That's the first quartile. If I ask you to find the median, you can also find the median. Find median. You will solve this equation. Capital F of median equals half. So 5 times median minus 4.9 equals half. So median will be 4.9 plus half over 5. Should be 5. And so on. You can find any percentile. This is continuous uniform distribution. The only trick I see from this kind of distribution, let me take you back. This part, the C on your screen, this will be given in the formula sheet. Everything you see on your screen at the moment, this will be given in the formula sheet. That's the first row of your formula sheet for the continuous distributions. Although the name will not be given, but you should be able to recognize from the formula sheet which one is continuous uniform distribution. Now, using this formula sheet, the only trick I see from this continuous uniform distribution, in most parts you will see in the question will tell you that X has a continuous uniform distribution, but if it doesn't tell you and you see that the density of the variable is constant, look at the density of this variable. Look at the yellow highlighted part. The density of the function is 5. Sorry, the density of the variable is 5. F of X is 5. It's a constant value. So whenever the density of a variable is constant value, it is uniform. The uniform distribution has another name. It's called rectangular distribution. It has a shape of like rectangle. If you plot this density on a graph, you will see the graph will look like this. If you plot f of x, small f of x against x, from 4.9 all the way up to 5.1, and you have like 1, 2, 3, 4, and 5, and let us say 6, you will see it will be like this. 5. F of x is 5. A straight line between 4.9 and 5.1. And the total area under this curve is 1. So the overall density, it looks like a rectangle. That is why this distribution is also called rectangular distribution. Rectangular distribution. Any question from continuous uniform distribution? Okay, what if I ask you to give me the probability for the same question, this question? What if I ask you to give me just a small tricky question for your interest? If I ask you to give me the probability of x less than 4.5. What will you do, Amjad Ammar?
0.
Why 0?
Because the probability begins higher.
The probability begins with 4.9. This value is outside the domain.
Yes.
This probability is 0 straight away. You don't put capital F of 4. You don't. This is capital F of 4.5, but capital F below 4.9 is 0. You will not put it like 4.5 minus 4.9 multiplied by 5. If you do like this, you'll get a negative probability. This is wrong. What if I ask you to give me probability of x greater than 4.5? Muhammad Faris.
We put it in interval.
Give me the final answer. Final answer. Probability of x greater than 4.5.
1 minus f 4.5.
And final answer?
Final answer, I don't know.
Muhammad Shafiq.
It will be 1.
It will be 1. All the values of x are above 4.5. So for sure, x will be more than 4.5. Similarly, if I ask you to give me a probability of x less than 5.5, what this will be? Ali Abdul Rauf.
It will be also 1.
1 or 0?
No, 1.
1.
It's bigger than 5.5.
Yes. What will be greater than 5.5? Amjad Ammar.
0.
0. What will be the probability of x between 4.95 and 7? Amjad Ammar.
0.75.
Point?
75.
0.75. Yes. 0.75. Don't plug in the value 7 in CDF. You will get something wrong. Because x cannot be more than 5.1, so the interval 5.1 up to 7 is useless. So this is equivalent to the probability of x between 4.95 and 5.1. Forget about the remaining part. So first you will write it like this one. This is equal to probability x between 4.95 and 5.1 plus probability of 5.1 to 7, and this part will be 0 because it cannot be more than 5.1. So you will solve only the first part. Okay, these are small tricks that that you may see in exam. Muhammad Faris.
Doctor, I don't understand what the difference between these types and the above.
And the above is what?
Like
In the above, I said you directly plug in the values in the CDF. In the above, all the questions, the values were within the domain. These values I'm giving you outside the domain. I'm training you how to handle the values outside the domain.
Yes, x greater than 4.5. We have a question.
Greater than 4.5. If you put the value 4.5 in CDF, you will find something like more than 1. Probability cannot be more than 1.
And above we said x greater than 5.01.
5.01 is within the domain. Now I'm talking about 5.5. This question.
No, here the vi. We have bx greater than 4.5.
Greater than 4.5 is also outside the domain. This one. If you put directly this value in the CDF, you'll get strange answers. So if a value is outside the domain, don't use CDF. Use your brain.
Yes, I understand.
Okay, let us move on to the second probability distribution, second special probability distribution. The second special probability distribution is called, which way should I go? I think I should start with, let us say exponential distribution. Okay, let me go with exponential distribution. The second special distribution is called exponential distribution. A random variable is said to have following an exponential distribution if its probability density function has this form. The mean of such variable is given in the formula sheet. It is 1 over lambda. The variance of such variable is given in the formula sheet. It's 1 over lambda square. And the CDF of such variable that is also given in the formula sheet. It is 1 minus e to the power minus lambda x. This whole thing will be given in the formula sheet. The most common application of exponential distribution is You will find a time until success, but it's not necessary that always time until success is exponential. So most of the examples you see for exponential distribution, you will see there will be time between the events, time before you get a success. Let me bring an example from exponential distribution. Okay, let us read this question. This question says that in a large corporate computer network, users they log on to the system. User logons to the system can be modeled. No, not this one. Let me bring a direct question from exponential. And then I will tell you what is the link between exponential and Python. That will come later. Let me bring a direct question from Python. Here is a question. In this question, it says that the time between calls to a plumbing supply business is exponentially distributed with the mean time between the calls to be 15 minutes. Now, if you look at the thing that I give you in the formula sheet here, when I tell you exponential distribution, the only unknown constant in the exponential distribution function is lambda. That's the only unknown thing you need to identify from the question. Like in this uniform distribution, if I tell you X has a uniform distribution, to write the probability density function of uniform distribution, you need B and you need A. And those B and A are somewhere given in the question. So you need to identify these parameters of distribution, A and B. There are two parameters of uniform, A and B. You'll get them from the question. Exactly similarly, exponential distribution has a single parameter, that is lambda. You need to get this lambda somewhere from the question. And this lambda is basically the average number of successes per unit. This is similar to the lambda of Python distribution, but later I will go into that story. So let us read this question and try to identify the value of lambda from the question. It is very clear from the question that X has an exponential distribution. They use the word exponential, and most of the times they will use the word exponential. With the mean time between events to be 15 minutes. Average time between the calls is 15 minutes. So lambda directly is not given. It is given obviously that X has an exponential distribution, but lambda is not given directly. Can anyone tell me what value of lambda is given and how is it given? Ali Abdul Rauf.
He gives us the average, which is 15
He gave
minutes.
you mu is 15. So how do you find lambda from this mu?
We use the formula, which is 1 over lambda.
You use the formula that mu x is 1 over lambda, and this is given to be 15. So that means lambda is the reciprocal of 15. Lambda is 1 over 15. Very right, Abdul Rauf. So your x follow an exponential distribution with lambda equals 1 over 15. This is the probability density function, 1 over 15. Lambda times e to the power minus lambda of x. Just plug in the value of lambda into the probability density function that is given. Similarly, I can write the CDF expression. That is 1 minus e to the power minus lambda x. Similarly, if they ask me to find the variance, I can find. I'm not going into that story. Let's go to the question. What is the probability that there are no calls in a 30 minutes interval? Now, what is the question here? Leave part A and B. I will get back to part A and B and talk about part C and D of this question. Part A and B is something we have already done, and I will get back to that. What is the probability that the first call arrives within 5 and 10 minutes from the opening? Now, is this question about time until first call? Your x is time until first call. Here, your x is time until first call. And time obviously is continuous. And this continuous random variable has an exponential distribution with lambda equals 1 over 15. You already wrote the probability density function. You already wrote the CDF. Now they're asking you to find the probability that the first call arrives within 5 to 10 minutes. Now the first thing you need to see is what is the variable that the question is asking you to find. The question is about the time. The question is about that the time is between 5 and 10 minutes. So how do you find it? Simply capital F of 10 minus capital F of 5. You have capital F. So that is 1 minus e to the power minus 1 over 15 times 10 minus 1 minus e to the power minus 1 over 15 times 5. Which is going to be what?
Zero point 2031.
0.231. Can someone confirm the answer?
Yes, 0.2031.
0.2031. Okay, now I want you to read part D. Part D says, determine the length of an interval of time such that the probability of having at least one call in that interval is 0.9. What is this question asking about?
If of x equal 0.9,
This is obviously regarding a percentile. Which percentile? Is it the 10th percentile or the 90th percentile? This is regarding the value of x. Find the length of a time such that the probability of having a call within that time is 0.9. So this is regarding the value of x such that the probability of having a call is 0.9 within that time. Which percentile is it? Can anyone guess? Ammar. Amjad Ammar.
90th.
The question is regarding the 90th percentile. The question is like this. Probability of x less than equal to a, this is 0.9. And the question is asking about find this a. Find the length of the time, find the value of a such that the probability of having at least one call within interval is 0.9. So such that you should receive the call within that time. The probability of receiving the call within that time is 0.9. Within that time means that the time should be less than or equal to that value. So you have to solve this equation. This equation means you need to solve the 90th percentile. A is basically 90th percentile. So you can solve this equation because the left side is capital F of A, and this will be 0.9. You plug in the value A into the distribution function. Distribution function capital F of x is given in the formula sheet. It is 1 minus e to the power minus lambda times x. This is 0.9. And you can solve this equation for A. Anyone who can solve this equation for A and give me the final answer of A. So I have e to the power minus 1 over 15 times A. This is equal to 0.1. And that means minus 1 over 15 times A. This is natural log of 0.1. And A is minus 15 times natural log of 0.1. Now, before I go to the answer, A is a value of x. This A is a value of x such that 90% density is below it. Now I have a question. A is a value of x and x is time. Time cannot be negative and you got A to be negative. Where is the problem?
Doctor, could you repeat your question?
The question is, we found the final answer A to be minus 15 times natural log of 0.1 and this is negative. Can you see it is negative?
Yes, but
A is a percentile. A is a percentile of x. X is time. So time, we are saying that 90% of the times you will have an event happening within this time period. And the time period is minus 15 times natural log of 0.1 minutes. Can time be negative?
the len will cancel the negative.
The natural log will cancel. Yes, Muhammad Ali.
Yes, I agree with him.
Ali Al Hassan.
It will cancel by the.
It will cancel. The final answer is positive. Your A is what? Give me the final answer.
34.539. No, 53988.
5388
Yes.
minutes. So there is a probability, 90% probability that you will receive the first call within 34.5388 minutes. That was the question. There is a 90% probability that you will receive the first call within how many minutes? Within 34.5388 minutes. That's the answer. Muhammad Faris, do you have another question?
Yes, please. If he asked the exceed 0.9, the percent will be 0.1, right?
We'll talk about this exceed and exceeded by later. This is confusing, but I'll talk about this one later.
Okay.
These two words are confusing, exceeds and exceeded by. I will talk about these words later. For now, if you have any question from part C and D, let me know. These are straightforward questions. Now I'll take you back to part A and B. And I'll show you these are not the questions from exponential distribution. Look at the questions. And these questions, you have solved these questions before. What is the probability that there is no call within 30 minutes? Is the question about time until first call, or is it about number of calls? Muhammad Faris.
Number of calls.
It is about number of calls. And is number of calls discrete or continuous? Number of something, is it discrete or continuous? In the previous chapter, we studied that number of something is always discrete. Ali Abdul Rauf.
I think it is discrete because you
It
have
is
0 calls.
Yes, number of something is always discrete. And in the previous chapter, we studied that number of successes per unit is a discrete random variable that follows a Poisson distribution. Number of something per unit, and the unit in part A is per 30 minutes. So these are not the questions from exponential distribution. These are straight away questions from Poisson distribution. You have solved these questions in chapter 3. The part A question is about number of calls. It is not about time until the first call. It is about having no call within 30 minutes. So here you define another variable, let us say x1, that is number of calls per 30 minutes. And here x1 follows a Poisson distribution with lambda equals, what is the average number of calls per 30 minutes? Who can tell me the lambda of this Poisson? Average number of calls per 30 minutes. The average number of calls per 30 minutes. Muhammad Ali.
3 multiplied by 15.
2 multiplied by 15?
3 multiplied by 15.
3 multiplied by 15. Why?
Oh, sorry, 2.
2 multiplied by 15. Why?
Because we want to change the unit from 1/15 to 1/30.
Okay, let us take more opinions. Ali Abdul Rauf.
I think it's 1/30.
1/30. Okay, Muhammad Faris.
2.
2. Anyone else?
Because we have Amin, a course of 15 minutes.
Yes, Muhammad Ali Al Hassan.
2.
2. Okay, anyone else? We are talking about average number of calls per 30 minutes. The question says that the average time until a call is 15 minutes. So in 15 minutes, you are having 1 call. In 30 minutes, on average, you will be having 2 calls. The mean time is given 1/15. That is 1/λ. This 15 is given as 1/λ. The reciprocal of this thing is lambda. Lambda is 1/15. Sorry, is it? 1/λ is 15. No, 1/λ is 1/15. This is lambda directly, is it? Lambda equals 1 per 15 minutes. That's given in the question. But we have a question regarding per 30 minutes. So lambda will be 2 per 30 minutes. So you can simply solve the question. What is the question? Having no call in 30 minutes. So probability of x1 equals 0. You just plug in x equals 0 inside the function. E to the power minus lambda. Lambda to the power x over x factorial. So this is e to the power minus 2. Let us look at part B. What is the probability of having at least 1 call within 10 minutes? Now the question is about 10 minutes. Adjust the value of lambda per 10 minutes. Give me the lambda per 10 minutes. I'll define another variable x2. X2 is the number of calls per 10 minutes. Number of calls per 15 minutes is 1. Number of calls per 30 minutes is 2. What is the number of calls per 10 minutes? Average number of calls per 10 minutes. Muhammad Ali.
0.667.
0.667, and this corresponds to, is it 2/3?
Yes.
Yes, this is 2/3. So your f of the mass function of x2, which is Python, that will be e to the power minus lambda, lambda to the power x over x factorial. So here the question is regarding probability of at least 1 call. So we're trying to find the probability of x at least 1. And this is 1 minus probability of x equals 0. 1 minus e to the power minus 2/3. 2/3 to the power 0 over 0 factorial. So this is going to be 1 minus e to the power minus 2/3. These two questions were straightforward Python questions. They were not exponential. And now we come to a point where we need to see what is the link between Poisson and exponential. We have been looking for a few minutes now. There is a link between Poisson and exponential distribution. And here is the link. The link between the Poisson and exponential distribution is, we usually say if X is number of successes per units, we say X is Poisson. And if you define Y as time until first success, then Y is exponential. This is the link. And you're talking about the same success, any same event. And here lambda is the average number of successes per unit. In both of the questions, lambda is average number of successes per unit. Here X follows Poisson and Y follows exponential. So this is another trick. We may tell you that X has a Poisson distribution with this lambda and ask you the question about Y. And we may tell you that Y has an exponential distribution. The time until first success has an exponential distribution and ask you the question about number of successes. So in the next class, we will practice the flip questions between X and Y, where the information is given like in terms of X and the question is in terms of Y, or the information is in terms of Y and the question is in terms of X. So these two distributions are very closely linked to each other. I want you to look at the details of Poisson and exponential from the book before coming in the next class. We will practice a few questions from these two distributions in the next class. If you have any question from today's class, you may go ahead and ask the questions. If you don't have the questions, you can leave the session at this point.
Doctor?
Yes, Ali Abdul Rauf.
Yes, about part A. I don't get it. Why we have 2/30? Because he said that we won't get a call in 13 minutes. Why shouldn't we say that's 1/30?
The question says that the average time till the first call is 15. Okay.
Yes.
Average time until first call is 15. What is this 15? It is the mean time until first call. Right?
Yes.
And mean time mean calls, number of calls. Indirectly, I can write the same information as average number of calls per 15 minutes equals 1. Can I write the same thing in this way?
Yes, yes.
Yes. So lambda per 15 minutes is 1. The second one is in terms of lambda. The first one is in terms of time. And these two are same things. This one is given in terms of 1/lambda and this one is given in terms of lambda. Did you get the point or no?
Still, that I didn't get it. Why we have 2?
Wait.
No.
If I write like this one. Now you get or no?
Yes, yes. This
You
is
get it now?
Mm, no.
It says that the time until first call is 15 minutes.
Yes.
On average, you are getting a call in 15 minutes. How many calls are you getting every minute?
It's 1/15.
1/15, the reciprocal.
I think I get it. Yeah, I think I get it.
Okay, now this is your lambda per minute. Convert it to lambda
Yes.
per 15 minutes. Convert it to lambda per 30 minutes. Convert it to lambda per 10 minutes. Any unit you want to convert.
Okay. So we just use the 1/15 or the 15 and then convert it. I don't take the 13 as the new value for lambda.
Yeah, lambda can be any units. I directly converted to per 15 minutes. I should have done it per minute and then multiplied by 15. It was actually 15 divided by 15, not directly 1.
Okay, thank you.
Welcome. Any other questions?